Okay, so 1.4 is projection. So I'll show you what a projection is first, but it's really important that we get the vectors going in the direction we want them to go in for this section. So let's just look back at section 1.1 for a second when we subtracted vectors and saw what direction they were going. So if we had u and v, and we did u minus v, okay, where is that vector? So it forms a triangle, but which direction does it point? That's the important part. So it does form the triangle right here, but we need for section 1.4 to know which way the arrow points. So I find this confusing myself, so I'm guessing that a few of you will find it confusing, and I have to keep thinking about it every time. So let me show you what I do when I'm trying to figure out what way an arrow goes, okay, just in case you get confused at some point. So if we do u minus v, that means we go in the direction of u, so there's u, and then instead of, from the end of this, remember, this would be u plus v, and that gives us, we started here and we ended here, so that gives us that vector in that direction, u plus v. So if we were doing u minus v, we go u, here's our start, and instead of going over v this way, that would be plus v, we go in the opposite direction, over here. So here's minus v, and here's our end. So the vector started here and ended here, so it's like this. So what I do is I go u minus v is here, so that's like this, so the arrow goes that way. Did you see what I just did? I kind of draw it, and then I look, so I say u minus v that's started and ended, so that's this vector, and then I move it over to where I want it. So this is u minus v points towards u. If you're good at memorizing things, you just memorize that it points towards you. I'm not good at memorizing things. I have to kind of think about it and look at it to remember, so that's how I do it. Okay, so I'll go back. If you were doing, you know, if you wanted to draw the vector u plus 3v, and here's u, and here's v, u, and then 3v. 1, 2, 3. Here's the start. Here's the end. So that vector's like this. Right? And if you wanted to go minus, you would go in the opposite direction, and so on. But wherever you start and end, putting them all together in one line is where you draw your new vector. Okay, does that make sense? All right, so what if we wanted u minus 3v? Where would that be? So here's u, and v would go this way. We want minus v, so 1, 2, 3, minus v, minus v, minus v. That's minus 3v's. So here's our end, and here's our start. So that vector is here, start, and the end is 0. Okay? If they put a whole bunch of different vectors, u, v, w, then they could make all these different linear combinations and ask you for the vectors, right? And that's exactly what you would do, just keep going in the direction or the opposite direction, depending if it was plus or minus. Okay? So, a projection. So just like a projector, so a projection, let's say we have a plane and we have a vector coming out of the plane, so not lying on the plane. And we want to project that onto the plane. So think of the plane as this piece of paper, and the vector, now you won't be able to see because we're right over it, but you can sort of see two shadows there. But if there wasn't two lights, what would happen? It would cast a shadow down on the paper. That's the projection, the shadow. Okay? That's exactly what it is. So it's like you have a sun up here, or a light, shining down, perpendicular to the plane. Okay? So straight down. The vector right here is called the projection. So this is the projection. So what do we know about it? Sort of makes a triangle. So there's a vector going up. We don't know this one, but we could find it. How could we find that pink one if we wanted it? Subtract the two. And we'll need to go in a certain direction. That's why it matters. So you'll need to know which way to subtract them so you get the arrow going the way you want. Okay? Yeah. And I have to stop and think about it every time, and then you get the wrong answer, and so when you check your answer, it's probably that you subtracted something in the wrong direction. Okay? So you can get this one by subtracting. So if we had, for example, so let's just draw that right here. So let's call this U, and this V. And if this is U minus V, it points in the direction of U, that way, if we want it. Okay. Right. And I just looked because I wrote that up there. But if I didn't just write that a minute ago, I would still have to go U minus V, it goes this way, and then draw it in. Okay, so we can find the other side if we know two sides. Okay. So the way this works is we project one vector onto another vector. So we project one vector onto a different vector. Rather than the plane as a whole, right? We would actually know what vector we want to project it onto. So you're given two vectors, and you want to find the projection. So the formula is this. The projection of U onto V okay. So I'll let you write that down. I'll write how you would read this. Projection of U onto V. So if we have U and we're projecting onto V, I'll just make V long so we can see it. So let's use a different color. So we project down, that's perpendicular. This piece right here is the projection of U onto V. Just that small piece of V. Okay? Now remember, a dot product gives you a number. So we've actually got a number over a number, so two dot products here. So this just gives us a scalar, some number. Say it was a half. This doesn't look like a half. Maybe this is a third of V. Do you see that? So for this projection, that number might be 1/3. 1/3 of V. What if the projection gave us a negative? What might that mean? This picture wouldn't apply. This looks like a third of V. What might a negative be, do you think? That the projection went in the opposite direction of V. So let's draw what that might look like. Say U is, let's make U go this way, and V over here. And the sun is shining straight down on top of U. So where does it project? So here's negative V. Do you see that would be negative? It goes in the negative direction. So here's our perpendicular line, and this little vector right here is the projection of u onto v. So when I read these, u is big, the same size as these letters, and v is like a little subscript. You know, like if you have a log down at the bottom of the G, it has a base, that's where this is. But I remember it's U is on top of V, so it's projecting U onto V. Now look at the formula. How many U's are over here? Just one. So if you're projecting U onto V, it's all V's in here except for that one, U dot V. So the formula is actually easy to memorize. If you're going U onto V, you want it to be a part of V. So V is over here. Okay. So what might this projection be? It might be, that looks smaller than a third. Maybe it's 1, 2, 3, say it's a quarter. This might be, so the projection of U onto V might be negative 1/5 of V. Or 1/4. If it was a quarter, right? Whatever size, I'm just guessing at the size. This projection of U onto V might be, what did we say, a third of V, but in the same direction as V. Do you see it? So negative would be the opposite direction. Could you have bigger than the vector? Could your projection be longer than the vector that you're projecting onto? Yes. Yeah, so if we had, well, let's make U longer and V shorter. You see the shadow would be beyond V. So here, let's extend V, drop that perpendicular line down, and this vector from here to here is the projection of U onto V. And what might that be? 2 times V, maybe, twice as long in the same direction. Okay, so, and we could have, you know, a longer vector in the opposite direction too if it was negative. All right, so if you had something like this, U and V was just short, and our projection goes from here all the way to here. So our projection of U onto, oh, I made it the same direction. Opposite direction would have to be this way. There's a U and a V. This is the same direction. I made them go the opposite direction, but this is still, how long does that look? Maybe 3 times? Maybe 4? Yeah. What about this one? So let's make that line bigger, V. If I project down, then here's the projection. Maybe it's, so it's negative, it's going in the opposite direction. 3, negative 3V. Okay, so that's what a projection is, so that's all the possibilities. Okay, so the types of questions we get with these is when you're trying to find like a perpendicular vector, you can do the projection. So if you wanted a perpendicular vector to V, you could do the projection and then subtract them and find that perpendicular vector. So there's a lot of subtracting, and it's because you're usually not trying to find the projection, you're usually trying to find the one that's perpendicular. Do you see that? Which is not the projection. The projection is actually on V, but if you wanted a perpendicular vector to V, you would project U onto V and then subtract U and V, and you'd get a perpendicular vector. So there's different things we can do like that. So, do we want the proof? Oh, let's do it. I'll have to draw a new picture for the proof. I know, you guys love proofs, right? I'm not going to test you on this, but I'll show you a little bit of the subtracting part. Okay, so let's just draw this normal one, U and V. And where's the projection? Is it smaller, bigger, in the same direction, opposite direction? Same direction and smaller. You go perpendicular here, and that's not the projection. That's just the line that drops down. The projection is actually right here. Okay, so let's call it P, just so that I don't have to keep writing projection for this example. Okay, so there's P. What is this side, the pink side? U minus P or P minus U, depending on which direction you want it to go. So let's say this is U minus P. Which way would it point? Towards U. So we go U minus P is this way, so it points that way. So U minus P points towards U. Okay. So we've got all three sides. So we have a side U, a side P, which is a part of V, and a side U minus P. Okay, those are our three sides. So the projection is giving a vector U minus P, which is perpendicular to V. Right? Isn't that what I just said? That usually we're using this to find the perpendicular vector to V. So this is saying that U minus P is orthogonal to V. So if we multiply this out, U dot V minus P dot V, and let's solve for P. No, I don't want to solve for P. P is the projection of U onto V, correct? So the answer is some scalar times V. All right, it's some multiple of V, either positive, negative, bigger than 1, less than 1, depending on where it is. So P is C times V. P is a vector, V is a vector, C is a scalar. So U dot V minus CV dot V equals 0. Solve for C. So what we were finding is a perpendicular vector to V, where P is the projection, which is just a multiple of V. And when we solved it, we got the formula for the projection. All right, so find the projection of U onto V. So we'll just do a formula first, then we'll ask all the complicated questions after. So it can be in R3 or R2, it doesn't matter. So the projection of U onto V. So U dot V over, we're projecting onto V, so that's all V's except for that one U. So V dot V. So we need to find U dot V. and v dot v. So it's negative 1/5 v. So you can picture the u and v must have been obtuse angles to project in the negative direction. So we could draw these. So u is 1 and 3. And v is 2, negative 1. Oh, I went down a little far, but it should have ended about there. Okay, and if we're projecting u onto v, they look almost perpendicular, but if we project that down, it must have ended up here at negative 1/5. So, does that make sense? So the actual projection, we could write it as a vector. So you'd multiply that in, because it's just a scalar multiple, so minus 2/5, and minus and a minus is a plus 1/5. So there's our projection, the actual vector itself, which is a portion of v, which we usually need that to do the subtraction, so you need to actually find the whole vector if you need to do something else with it. Okay, this answer is actually totally fine if you're just asked for the projection. 1/5 of v, you would need to write it all out because v is given here, so I can see what 1/5 of v is. But what we'll need to do is something else with that. Okay. So there's 3 types of questions we'll do. The first one find 2 orthogonal vectors m and n in the plane 2x minus y plus 3z equals 0. So just looking at this vector, we know that it goes through the origin, or the plane, because it has a 0. Alright, so we've got a plane. Don't try to put them in their actual place. Any drawings you do don't have to be accurate. Just, you draw 2 vectors, even if they're not even the same size. Once you find the projection, you might draw them the different way if it was supposed to be negative instead of positive. But so what we want to find is 2 vectors that are in the plane, so that lie on this plane, that are orthogonal. What vectors are we given in the question? You could find any vectors in the plane. You are also given the normal right off, that one you know. So we know the normal is what? 2 minus 1, 3. So we know that. All right? Which we may or may not need. But let's say we find how do we find any vectors in the plane? So what we want is M and N so that they're orthogonal. That's what we want. So let's find one vector in the plane, and then we're going to find the orthogonal vector to it. Does that make sense? So first find any two vectors in the plane. Now, if you lucked out and they happen to be perpendicular by fluke, then I guess you're done. All right, but I would want you to actually be using the projection for something. So, but whenever I do this, I always double check, because if they are orthogonal to start with, I'll take a different vector to illustrate, because that usually won't happen. How do we find two vectors in the plane? We already did it today, which is find 3 points and then the vectors between them. So to find two vectors in the plane, find 3 points. Is this the same one as we used earlier? It might even be. 0, 0, 0 is 1. And then if we plug in, say, x is 0 and y is 1. So we'll get 0 minus 1 plus 3z. Oh, let's do this. Yeah, exactly. So 0, 3, 1. And what did you say you did?
I did 0 and 0, and then I solved it. So it's like x was 0, y was 0, and z was 3.
No, because that would be 9. If z is 3, then you would get a 9 there. 3z equals 0 would give you z is 0. Okay, so another point, let's say x is 1 and z is 0. So you can do fractions if you want, and I said you could use just a regular scientific calculator. So when I was doing the homework today, I used a calculator because they're all fractions. All the questions they give, they don't work out really nice. The projections are all, like, some of them were 47 over 86. Like, they weren't nice numbers, so I just used the calculator to do the fractions, just to be quicker. Okay, so we've got 3 points. Let's label them A, B, and C. And we'll find AB and AC. Okay. So what might we do? So what we have now is a vector AB and a vector AC. I'll just draw it longer because it's easier to see. We have two vectors. But we want to find a vector perpendicular to one of these two, because we need two vectors, but they have to be perpendicular. So if we projected AB onto AC, we would get a vector in the direction of AC, and then we could find this to get the perpendicular one. You can't just subtract these because it wouldn't be perpendicular. That's why you need the projection, and then you can subtract them to get the perpendicular. So this right here would be the projection. AB onto AC. Okay, so let's do it. So this would be AB dot AC. We're projecting onto AC. So AB dot AC. And then AC dot AC. So the projection of AB onto AC is 6/5 AC. So my picture is actually a little bit wrong because this was bigger than 1, so AC was actually shorter because this went 1/5 more than the whole thing, but you don't have to go back and fix your picture. Your picture's really just an aid to know what to do. But 6/5 is bigger than 1, so it was 1/5 bigger than the whole. The other thing I want to comment on is to leave these with common denominators. Like if one of these fractions were able to be simplified, don't do it. If you've got 3 fractions and they're all over 47, leave them all over 47, don't simplify. Not that that would simplify anyway, but don't, because you need them later to add and subtract, and if you already have a common denominator, it's easier. Okay. So on my homework, you'll actually see that the calculator simplified, I wrote it down, and then I unsimplified it so that it was the same denominator. Okay, so if that's the projection, that's right here. And we want to find this one. Okay, so to get a vector that is orthogonal to AC, so we've got AB. AC we found was actually shorter. And the projection was a little bit longer than that. So this pink one is the projection. AB onto AC. Then this, yeah, it doesn't look perpendicular right now, but my bad drawing. So this, we can do, subtract either way, it doesn't really matter. So we can do, what are we subtracting? This is a projection vector that ends at the perpendicular line, and this one. So we want to do AB minus the projection. AB was 031, and the projection (3 minus 12/5), 15 minus 12, 3/5, and 1 minus 0. You could say the projection because that's in the plane as well, or you could say AC is orthogonal to, and how would you check? you would check the dot product is 0. AC was 120. So AC is orthogonal to that, but so is the projection, and that would also be in the plane. So you could say the projection's orthogonal to that, or AC, because the projection is just a part of AC anyway. So what you could do, like to study for something like this, is say if we wanted to find two vectors that are orthogonal in the plane, step 1 would be to find 3 points, step 2 to do 2 vectors between them, step 3 project one onto the other, doesn't matter which one, and then you need to make the triangle to find the other perpendicular one. So we want to find the distance from a point to a line. So we've got a line, and we've got a point that's not on it. Okay? And we want to find the distance. So what would the distance be? How would I draw that? What do they mean by the distance? In math, when you say the distance, you're not asking for just any distance. You're asking for a specific one. Which one would it be? The closest. So what is the closest distance? Is always the orthogonal distance, right? So it's asking for how long is that vector? Between A and some point here, let's call it P, which we don't know what that point is. Okay? So that's what we're looking for, is the length of this. The length of AP, or PA, whichever way we have it going when we draw it. Okay, so that's what we're looking for. Does that make sense? And then actually I said, and then find the point, so then we're looking to find what the point actually is at P. So what that closest point is. Okay, now what were we given? We were given a point that's on the line and the direction of the line. But that point on the line is probably not the closest point. So let's draw it somewhere else on the line. So let's call it B. And A is the point 1, 1, 1. And P is the point X, Y, Z. We don't know what it is yet. We're going to find what X, Y, and Z are. Does that make sense? So far, so good? So what could we do here? So we're talking projections. So we do know A and B, so we could find the vector between them. And then we could project that vector onto the line. We could find the vector between them, project it onto the line. Then we would know this. And then how could we find that one? It's the subtraction, which we usually have to do, so you have to subtract it. So once you know that in the projection, you subtract them, and you would get that, and then find the length of it. And we'll do something else to find what the actual point is. So this is where you have to be careful of which way the arrows point, because your projection, so let's draw the line between. I've got lots of colors going on. So here's my line between. Okay, so I want to make that into a vector, and I'm going to project it onto the line. So which way do I want my arrow pointing towards? Towards A or towards B? Towards A. When you're projecting a vector, it's going to point in the same direction, and it's really odd to have it pointing this way and then pointing that way again. Right, so you always point away. What you want is, when we draw U and V, to do any illustration, don't they meet here and the arrows point away from it? So they're meeting right here, so we want the arrows pointing away. Okay, so when we project A onto that, it will give us this. So the projection of, which way is this, AB or BA? BA, because the arrow points at the A, so it's BA, okay? So the projection of BA onto the line, let's call it line. There's a little, okay? Or direction, or U, or give it a name, whatever you want to call that vector. So I just called it a little line. Is equal to this vector. Which way is the arrow going to point when I do the projection? It's always the same way. So when I project that down, the projection is here. This will be the projection. Okay? And that's equal to the vector between B and P. Which way? BP or PB? BP. Okay, do you agree with that? Yeah, so when we find it, we'll know that. And if we know B and we want to find P and we end up knowing this answer, then we can solve for the other, which we'll get to in a minute. All right, so you really need to draw pictures for these, because then you can figure out what you're trying to do. So what do we want to find is the length of this. We have to start by finding the projection. So we need to find the projection of BA onto the line. So find BA. So that is A minus B. A is 1, 1, 1, minus B. I called this B. 1, 2, 3. Don't flip it around to get positive signs, because then you're making the arrows go the wrong way. Okay, does that make sense? So, oh, I scared you, I'm sorry. She touched her phone right when I said don't. And then she looked scared. I wasn't talking to her. Don't change the signs. Okay. And L is what? Is our direction vector from our line. Okay. So the projection of BA onto L is BA dot L over L dot L, and it's going to be in the same direction as L, or on the line. So BA dot L. So 0 minus 1 plus 2. L dot L. And I'm just doing the dot products quick, because you can get those dot products. That's not anything new. All right, so BA dot L is 1 over 6 of L. And this is what I'm talking about, that 2 over 6, you could write it as 1/3, but don't, because we want to subtract something with all these numbers, and it's better to be a common denominator. So just leave it as 2 over 6. Okay, so back to our picture, what is that? So what did we just find? We found this projection right here. Okay? The numbers don't make sense because this is saying 1/6 of the line, but the line so is obviously 6 times as long as that, right? I have it going in the same direction this is, so the picture could be okay for it, but don't modify your picture. You just, because the technique is the same whether it's going in the same direction or the opposite direction, you don't need to worry about that. So now what are we going to do? We wanted to find this distance, so we need to find that vector. And does it matter which way that goes? The arrow, if we're finding the length of a vector, does it matter if it points up or down, or would it still be the same length? Yeah. All right, if the vector is 1, 1, 1, or -1, -1, -1, it's still the square root of 3, either way. Okay? So, we need to find, what's this called? BA minus BP and I'm just calling it BP because that's easier than writing the whole projection thing. So we want to subtract those. So BA is 0, -1, -2, minus -1, -1/6, -2 plus 1/6, okay, so that's the vector itself, but we want to know how long that vector is. We want to find the length. So which way does that arrow go? Just the way I subtracted it, which way would it go? Pointing up or pointing down? Up, yeah. So BA goes this way, minus BP, so BP goes that way, so it goes here. So here would be the start and the end, so it goes up. So this is the point P, and this is the point A. So what is that line called? It starts at P and it ends at A, so it's PA. Right, just going with the points, this is PA and B. So instead of writing that every time, that's how we found it, by subtracting those, but it's the vector between A and P going in that direction. So the length of that so let me show you something here. Do you see they're all a common denominator? And you're squaring them all. So 6 squared is what? 36. And square root of 36? 6. Any common number like that, a common denominator, you can actually bring out as 1/6. It would always be positive too, because, right, you square the 36 and then take the square root of it. So that's a factor you can move out front. And that actually comes from that dot product thing again. If there's a common factor in it, you can do it after or before. So this would be just minus 2 squared plus minus 7 squared plus minus 11 squared. 4, which is what? 50, 60, 74, 174. Square root of 174 divided by 6. So approximately 2.2 units long, whatever the units are. So I just rounded it off. But you could leave it as a square root, of course. But now it asks for the actual point. So that's the distance. That was sort of part A, is how the distance from the point to the line. But we actually want to find the point. So I'm going to redraw my picture with what we now know. So I did it this way. This was our line, B, A, P. We have them all going like this. So the lines between them, this is BA, this is BP, and this is PA. And we know all of those vectors now. And we know how long the PA is, because that's what we were asked for. But we want to find P. So A was the point 1, 1, 1. And B was 1, 2, 3. And remember I said P is X, Y, Z. So if we know that PB is P minus B, the points, and we already have the vector PB, which is what? -2, 6, 1, 6, -1, 6. P we don't know, and B is 1, 2, 3. So once you have all the sides, you can find any of the corner points from that. Now, I noticed in the book they actually write out the parametric equations and then solve, but I would just rearrange this, like move this vector. It's negative on the right-hand side. Move it over here, so we have 2, 6, 1, 6, plus 1, 2, 3 is equal to X, Y, Z. Do you see what I mean? Just rearrange it and then solve. So X, Y, Z is 2, 6 plus 1, 1, 6 plus 2, and -1, 6 plus 3. 12, 13, and 3 is 18 minus 1, 17. You'll have to go back and look through all of that because it's like super long and confusing. But what you really need to do is draw the picture and try to label each side. So draw the picture huge if you want, and if you label each side, it'll keep things straight. Remembering if you have 2 points, you subtract them to get the vector in between. So if you know 2 points, you can find that vector. You can find the projection to get that orthogonal one, and you subtract 2 to find the vector between them. So we're going to do a similar question to that. What time is that? 6:30. So we'll do a similar question to that, except a distance from a point to a plane and the closest point. So that was the distance from a point to a line. And a point to a plane is easier. Oh, it sounds like it should be harder, it's actually easier. So find the distance from the point to the plane and the closest point. So instead of just drawing a line across the page, is what I started with last time, we would draw like a plane. And then we have a point somewhere that's not on the plane. Don't draw it yet, because I always have to redraw it. I'll tell you what I make a mistake with. So what do we know about the plane, just given this equation of the plane? What do we know about it? What can we read off of that right away without doing anything? The normal vector, which is what? 2, negative 3, 1. Okay, so we know the normal vector, which is where on that plane? Well, it could be pointing down, but we'll pretend it's pointing up. Anywhere, actually, because it's perpendicular to every vector in the plane. So we could draw it here, but we could also draw it here, we could also draw it here, we could also draw it here, because we don't know if it's up or down, and it would just be multiple. But all of these are the normal vector. Remember, a vector isn't fixed, right? A vector is just like that toothpick that you can move around as long as it's in the same direction. Okay, so now we're going to redraw that because we don't want all those vectors sticking out. We just want one. We're not actually going to draw that yet. Let's draw the point A. And the normal vector that's right attached to it. Because wouldn't a normal vector go there? But what? It's probably not the right length yet. Right? The actual normal vector might be too long or too short. So let's draw it too long. Okay, so there's the normal vector. And our point is somewhere, and we want to find what? We want that distance. So we actually want to find this distance. And so I put find the length of this vector. Let's call this point P, because we need to find it later anyway. Does that make sense? So I drew a normal vector going through the point that I had, because I could draw that normal vector anywhere. So here's our point A, is right here, somewhere on the normal vector. The normal vector could be shorter, but we just draw it longer to make it look easier. So we don't know P. And when we find a point on the plane, we could fluke and find the right point, but doubtful. Right? It is possible, though, that you find the right point, but we'll pretend we didn't find the right point, even if we do. So what we need is a third point to make that triangle. So let's find any point on the plane. We'll call it B. And once in a while, someone will accidentally find the right point. Yeah. So B, so we want any point on the plane. So we have 2x minus 3y plus z equals 2. So it doesn't go through 0, 0, 0. Let's plug in 2 zeros. Z would be 2. So 0, 0, 2. And remember, subtracting things and multiplying things with a bunch of zeros in it is easier. So it's good to plug in a couple zeros instead of ones and things. All right, so we've got a point B. We're going to say it's 0, 0, 2. And now what might we do?
Find the vector between B and A.
Sure. Find the vector between A and B. In which direction? Pointing towards A or pointing towards B? Towards A. Because we're going to project it. Oh, wait, no. No, you're right. I'm wrong. whoever confused me, I think you're right, and you're wrong. I'm wrong. We want it to point towards B. Where are we going to project it? Are we going to project it onto the plane, or are we going to project it onto the normal? Where are we projecting it? Onto the normal. We don't actually have the vector in the plane. When we had a line, that was this one we knew. Here we know this one, and remember you want their two tails to attach when you project. So which direction do we want this vector to point? That's attaching to the normal there, so it's going to point towards B. And then this one will point towards, so it'll be that vector in that direction. So we want their tails to attach. So whatever you're projecting it on, they need to attach, and they both point in the opposite direction. You know, when I was in school, I hated when profs did these things with their hands, because I said, oh, I went to class and I felt like they're doing all these things. Did you ever take a second-year calculus course? Anyone? And they start doing this? Showing you how to draw the 3D plane. I never got that. But now I do these weird things too, so I apologize. All right, so we want them to attach and point away from each other. So now what we're going to do is project. So this will be the vector AB. Arrow goes to the B. So AB, we're going to project AB onto the normal. And that will give us this vector that we want, which is the vector between A and P. So to label it, what would we call it, AP or PA? AP. So it'll give us AP.
How do you know it's projecting from the normal?
We're projecting it onto the normal. We're doing that on purpose because we want to find this length. That was the goal. So if we know any other vector, we can project it onto there, and that'll give us that exact piece of the normal that we need, the right length. Yeah, because that will do this perpendicular thing, right? And that'll give us this piece, the projection, which is what we're looking for. Yeah. Okay, so let's do the projection. So we need to find A, B, and N. So I'm just going to redraw this. So this is A, this is B, and this is P. So we want A, B. Minus 1, minus 1, 2 minus 1 is 1. And we're projecting it onto the normal, and we know the normal from reading it off of the plane that was given. And so the projection of AB onto the normal is AB dot normal